Okay, so U substitution with definite integrals works very similar to just how we did definite integrals. Let me bring this into focus. All right. So let's just start working examples and we'll see what happens. So when we did U substitution, we generally said that if we have a polynomial expression, we want U to be the expression whose derivative is everything else. So we're going to make our U x squared plus 1. And we're going to make our du 2x dx. Now we want to replace x dx, which means that 1/2 du is x dx. Now the great thing about U substitution is that we don't actually have to go back to x's once we do our substitution. What we should do is substitute in our x limits so that we get new u limits. So x goes from 1 to 2. If I substitute 1 into this, that means my u limits would be from 1 squared plus 1 is 2, and 2 squared plus 1 is 5. So when we rewrite our integral, we're going to have an integral from 2 to 5. We'll just put the 1/2 in the front, and we'll have 1/2, what's it, just u cubed du. So when we integrate this, we will get u to the 4th over 8 because of the 1/2. And we'll evaluate that from 2 to 5. So 5 to the 4th is 625 over 8 minus 2 to the 4th is 16 over 8. So this is 609 over 8. What's that like? I have no idea. 609 divided by 8, 76.125. So we learned that we can integrate using our calculator. So we're going to have x times x squared plus 1 dx. And let's see what we get. 76.125. Example 2. So we want u to equal 1 plus 2x squared. Du would equal 4x dx. So 1/4 du is x dx. Because again, we want to replace x dx. Our x limits are from 0 to 2. Our u limits would be from 1 plus 0 is going to be from 1 to 2 squared is 4 times 2 is 8 plus 1 is 9. So we can rewrite this as 1/4, the integral from 1 to 9 of, this is going to be u to the negative 1/2 because I will rewrite this. So that's a 1/2 on the bottom, right? When we move it up, it's going to be u to the negative 1/2 du. And when we integrate, we'll get u to the 1/2 divided by 1/2, which is the same as multiplying by 2. So you know what? Write it out. So 1/4 times 2u to the 1/2 evaluated from 1 to 9 simplifies to be 1/2 u to the 1/2 evaluated from 1 to 9. Um, let's see. So 1/2. The square root of 9 is 3. The square root of 1 is 1. So 3 minus 1 is 2 times 1/2 is 1. We could have done this as 1/2 times 3 minus 1/2 times 1, which is 1.5 minus 0.5, which is still 1. Example 3, when we have a basic trig function, we wrote this rule in class. Let's see if we can quickly remember it. We said the antiderivative of sine kx is negative cosine kx over k. All of this is divided by k. So that's still going to be true. We should get negative, we'll do this two ways. We should get negative cosine 3x over 3. We need to evaluate from pi over 12 to pi over 9. So this would equal negative cosine. So 3 times pi over 9 is 3 pi over 9, which is pi over 3 minus, so this should still be divided by 3. So negative cosine pi over 3 divided by 3 minus negative cosine. So 3 times pi over 12 is going to be 3 pi over 12 or pi over 4. And all of this is divided by 3. So that's really just plus. So the cosine of pi over 3 is 1/2. So negative 1/2 divided by 3 is negative 1/6, plus the cosine of pi over 4 is the square root of 2 over 2 divided by 3 is the square root of 2 over 6. So who knows what that is? So negative 1 plus square root of 2 and divided by 6 is, we'll say, 0.069. All right, so that's what we got when we integrated without doing U substitution. So if we did U substitution, U would equal 3x and du would equal 3dx. So 1/3 du equals dx. The x limits are from pi over 12 to pi over 9. Our u limits, 3 times pi over 12 is pi over 4. And 3 times pi over 9 is pi over 3. So when we rewrite this integral, it's going to be 1/3 the antiderivative from pi over 4 to pi over 3 of just sine u, right? So we'll get negative 1/3 cosine u evaluated from pi over 4 to pi over 3, not pi over 9, so pi over 3. And so from here, we would get exactly the same thing that we did right here. It's just two ways of verifying the same result. Example 4, we have sine cubed cosine x dx. So we want our u to equal sine because it's the thing cubed and its derivative is cosine. So u is sine x dx and du is cosine x dx. Our x limits I should point out cosine x dx is a direct substitution for du, so we don't have to do anything. Our x limits are from 0 to pi over 6. The u limits are from the sine of 0 is 0, and the sine of pi over 6 is 1/2. So when we rewrite our integral, it's the integral from 0 to 1/2 of just u cubed du. I'll bring that into focus. So when we integrate this, we will get u to the 4th over 4 evaluated from 0 to 1/2. And so 1/2 to the 4th over 4 minus 0 is, well, 1/2 to the 4 is 1/16, and then divided by 4 is 1 over 64. So this is something we could verify on the calculator. So we'll do math, 9, 0 to alpha equals, so we'll do pi over 6. Hey, let's make, so we are in radians. So from 0 to pi over 6 of, we're going to do sine x, and we need to cube that. We're going to have cosine x, and we'll put a dx, and as a fraction, it's 1/64. So again, the calculator is a way to verify that our area is correct. So for example 5, we have the graph of x times the square root of x squared plus 1 from 0 to 2. So when x is 0, that's going to be 0. When x is 2, 2 times the square root of 5. So 2 square root of 5. We'll just say that's it. Who knows? We're trying to find this area, which is just a definite integral from 0 to 2. So we're integrating from 0 to 2 of x times the square root of x squared plus 1 dx. U would equal x squared plus 1. Du would equal 2x dx. So 1/2 du equals x dx. Let's see. So we would have 1/2 the integral. Our u limits would be from 1, and if you substitute in 2, be formal. So from 0 to 2, u goes from 1 to 2 squared plus 1 is 5. And x squared plus 1, the square root of it is the same as having this to the 1/2 power. So when we integrate, we're going to have 1/2 u to the 3/2 divided by 3/2 evaluated from 1 to 5. That's the same as multiplying by 2/3. So we're going to have half of 2/3. So 1/3 u to the 3/2. My bad, you can see none of that. Evaluated from 1 to 5. So when we substitute in 1, we'll just get 1. So alpha y equals 1/3 5 to the, what's it, 3/2. So when we substitute in 1, we'll get 1/3. So minus 1 divided by 3. And this is not a rational number because the square root of 5 is not a rational number. So minus 1/3, 5 to the 3/2 equals what, 3.39. And also, that's something that we can verify straight from the beginning. We go math 9 from 0 to 2 of x times the square root of x squared plus 1 dx. We get the same thing. All right, so for the last example, we're going back to Riemann sums for a moment, just as a quick review. It wants us to use 4 subintervals to find a left Riemann sum to approximate this. So remember, for left Riemann sums, in this case, since we have 4 subintervals, we have one subinterval that has a width of 5, another one that has a width of 4, another one that has a width of 6, another one that has a width of 5. So those are our 4 subintervals. Left Riemann sum means use the 4 left y values or r values, and we just match up the interval with their y value. So we're going to have 5 times 14, 4 times 18, 6 times 20, and 5 times 27. So area is going to equal, all right, so the water being pumped. So we'll say this equals 5 times 14 plus 4 times 18 plus 6 times 20 plus 5 times 27. So 70 plus 72 plus 120 plus 135. That's 142 plus 120 was at 255. So this equals 397. You might want to check me. I don't know. So right endpoints are using the right 5 y values, basically excluding the first. So the area is going to equal 5 times 18 plus. Now we expect this to be an overestimate because the function is increasing. We notice that the values strictly go up. So 5 times 18 plus 4 times 20 plus 6 times 27 plus 5 times 32. So 90 plus 80 plus 162 plus 160. What's that? 170 plus 322. So 492. All right. So that concludes this video on definite integrals with U substitution.